we could go ahead and get started. So thanks everyone for joining today's session on Uber's batch analytics evolution from Hive to Spark. We have Kumandini here from Uber who's going to be leading the session. So Kumandini, you want to take it away?
Yeah, thank you. Hi everyone, thanks for joining. I'm Kumudini. I work in batch analytics team at Uber, and today I'll be talking about Uber's batch analytics evolution from Hive to Spark. So this is going to be the agenda for today. I'll first talk about, I'll give an overview of Hive and batch analytics at Uber. We'll talk about what was our motivation to migrate from Hive to Spark, what was the migration strategy that we took. Then we'll dive into details around how did we do the automated Hive to SparkSQL translation, the shadow testing and data validation framework that we built. And then we'll talk about the challenges that we faced because of disparity between Hive and Spark, and finally the results and future work. So this is the overview of batch analytics at Uber. At the engine layer, we had both Hive on Spark and Spark. On top of Hive on Spark, we had Hive ETL workflows as well as the interactive workloads. On top of Spark, apart from Spark ETL, we had AI and ML platform, notebooks, ingestion, etc. All of these together power various use cases at Uber, like compliance and financial reporting, planning and forecasting, fraud and risk analysis, etc. This was the scale of Hive at Uber. We had around 18,000 total ETL workflows, which contributed to about 5 million monthly scheduled queries. We also had about 150K monthly interactive queries. All of this together contributed to about 35% of total YARN usage at Uber. We were primarily using Hive on Spark, and the versions that we were on was Hive 2.3 and Spark 2.4.3. Let me now give a quick overview of what Hive's architecture at Uber looked like, since it was a bit different from what is present in open source. So first we introduce this concept of a payload. Payload is a set of Hive queries which are run as part of a single Hive on Spark job. These can be a combination of DDLs, DMLs, and create temporary table kind of queries. Each task in a workflow DAG can submit multiple of these payloads. Then we also introduce something called Hive proxy, which is a REST proxy to run Hive payloads asynchronously, right? So it does the Spark submit to YARN instead of submitting it to HS2, right? So this helps us have zero downtime Hive releases, and it also has config guardrails and transformations in place. The Hive on Spark job then executes YARN. So it executes each SQL statement in the payload sequentially. The entire query planning for the SQL happens within the driver. It's also responsible for sending out the heartbeat back to the proxy, which can then be polled by the workflow client. So what was our motivation to migrate? So Hive on Spark has become obsolete and inactive in OSS, while Spark 3 has a very vibrant OSS community. Performance-wise as well, Hive had static query planning, while Spark 3 onwards, we have AQE, which gives better compute and cost efficiency. And as I already showed, we had Spark on the engine layer already. So we wanted to unify all the batch analytics under one single engine. We also had a lot of observability and performance optimization tools already built and integrated with Spark, and had we gone with another engine, we would be doing that work again. Talking about the migration strategy that we took, so as I already mentioned, we had about 18,000 workflows, and these workflows contributed to about 50,000 unique payloads. And these were distributed across hundreds of teams at Uber. So had we gone with a decentralized and a manual migration approach, it would have taken a very long time. So we decided to take a two-step migration approach, where first step was to do an automated migration, which involved translating the Hive payload into SparkSQL in an automated manner. validating it using shadow testing, and then migrating the payload. Second step, after the migration, the payload was migrated, the second step was updating the source code. So for these, we provided some automated tools, automation tools to update the static HQL in the code. And for the cases where HQLs are generated dynamically or programmatically, we work with the workflow owners to update the source code. So we introduced a shadow testing framework, which basically intercepted all Hive payloads submitted at the Hive proxy layer, right, and translated it into SparkSQL, validated it in an isolated way in parallel to the Hive run. And once the shadow testing was done, next time the workflow was submitting a Hive payload, it would directly be translated into SparkSQL and run on Spark instead of Hive. Now let's take a deeper look into how we did the translation. So for translation, we leveraged LinkedIn's open source service called Coral. We leveraged its framework. We could not use it as it is. For example, Coral did not support Hive 2x grammar. It only supported Hive 1, so we added support for the same. We also got rid of dependency on Kelside's rel node. This is because not all the constructs in SparkSQL and Hive can be expressed in a rel node. So this meant that we did not do any query optimization or any semantic validation in the translation process. Apart from that, we added support for DDLs and unregistered UDLs. And lastly, we added support for the entire payload translation and not just the query translation. Here's an example of a Hive payload being translated into a Spark payload. So this Hive payload is translated to this Spark payload. So if you see auto convert join configs are translated into auto broadcast threshold in Spark. And if you look at the query, the struct built in is translated into named struct with the column names being the default column names that are generated by struct in Hive. So let's take a deeper look into how this translation is working. So given the input Hive query, we parse it using Hive grammars into an abstract syntax tree. Now this AST is then converted into a language agnostic internal representation that is a SQL node tree. So if you see here, the struct is translated into row, which is a language agnostic concept. Now this SQL node tree is traversed in a pre-order manner and each node is transformed into SparkSQL compatible SQL node. So this becomes this SparkSQL compatible SQL node tree. Here you'll see that row is transformed into name struct and all the corresponding arguments are also transformed accordingly. Now this tree is again traversed and each node is then converted into the corresponding language string. So we get the output SparkSQL query. So once the translation was done, next step was to validate it against the production Hive payload. So for this, we built the shadow testing framework, and here's what it did. So it intercepted the Hive payloads at the Hive proxy layer. So once a Hive payload was submitted to Hive proxy, it translated it into SparkSQL. It also ensured that this translation was safe, which means that all the output data sets were replaced. Right? Then it submitted it to Yarn and waits for Hive production run and the SparkSQL shadow run to finish. Once that is done, it triggers the data and performance validations against the Hive run. And once that succeeds, it checks whether it has validated this particular payload enough number of times. It does that by using payload fingerprinting. And if it has, it marks the payload fingerprint as ready to migrate. And once all the workflows belonging to that, all the payload fingerprints belonging to a particular workflow are marked ready to migrate, the workflow is marked ready to migrate. A bit about what safe translation looks like. So this is a Hive payload. right? Now it's creating a table, then reading from that table and writing to another table, and then it's reading from the temp table that was created, and then writing to the destination table, right? So first thing we do is we replace all the output tables here, with the corresponding shadow tables, right? And the next thing that we do is, if a table is being written to, the subsequent reads also happen from the shadow table, right? So since temp table was written to, the subsequent read was also replaced. And then if there is a table that is being written to and its DDL is not present in the payload, we also add the DDL with create table like statement. So this ensures that the insert statement doesn't fail with table or view not found. So there were a few limitations of the entire shadow testing process. First being the race conditions. To take an example, so if you look at this payload, we are creating a table on top of a HDFS location, then reading from it and then dropping the table, right? So when this runs in mode, so when this runs in shadow mode and it tries to read from source table, it fails with table or view not found. So these kind of failures were intermittent, so we did not really solve them. We just ensured that we had enough runs of these payloads via shadow testing, and as soon as we got a couple of successful runs, we migrated the payload. Secondly, load data queries. So load data queries basically move an external file into the table location, right? So these also failed in shadow execution because the file was not present in the original location, and it failed with file not found exceptions. So for these kind of queries, we modified the query plan in Hive a little bit to first copy it to a temporary location and then move it to the table location. And in translation, we use that particular temporary location so that it's available or it's accessible via the shadow run. Lastly, we faced issues with schema mismatches. So this happens when the DDLs in the source code are not updated. So we end up creating shadow tables with an outdated schema, right? And any subsequent reads or inserts to that table fail because of that. So we identified these kind of scenarios from the failure logs and configured the schema statically into the shadow testing framework. And next time the payload was run, it used the correct DDL. So we appended the correct DDL to the payload. Yeah. So once both Hive and Spark runs have finished, we trigger the data validation between all the output tables of Hive and Spark payloads. And here's how we do the data validation. First, we compare the row counts between the two. And then we compute row checksums and take 10% or sample 10% of the rows from both the data sets, and then compare those checksums using symmetric difference, which ensures that the comparison is order agnostic. Again, there were a few challenges with this kind of data validation, first being the floating point arithmetics. So whenever there was an aggregation operation or any kind of arithmetic on floating point or double columns, there was a rounding error which caused data validation failures, and those are mostly false positives. So we took a number of measures here. First being, we just tried to round such columns to a certain precision before computing the checksum. So this helped but did not entirely solve the problem. Secondly, we added a tolerance of about 1%. So that means that even if 1% of the rows are mismatching, you would still go ahead and mark the data validation as successful. And thirdly, we had to add the column level checks as well, where we compared the maximum difference between the entire column across all rows. And if it was less than a certain threshold, we marked the data validation as successful. Another issue that we faced was stringified JSONs being stored in string columns. And to solve this, we wrote a custom UDF which was applied to all the string columns before computing the checksum, which basically created an ordered JSON out of the string column. There were also non-deterministic functions like collect list, collect set, or random row number, these kind of functions which caused data validation failures. We simply had to identify such columns and exclude them from data validation because it doesn't make sense to compare them. And lastly, in case of frequently updated input data sets, we saw some race conditions because of which Hive and Spark output differed slightly, right? And this caused row count mismatch mostly. To solve this, so we saw this only for about 2% of the total workflows at Uber, and to solve this, we had to snapshot the input data sets for such workflows and run both Hive and SparkSQL on them and then compare the output. So this was slightly expensive in terms of compute as well as storage, but since this happened only for the 2% of the workflows, we were able to do it. Now we'll talk about the failures that we saw at various stages because of the difference or disparity between Hive and Spark, and how did we bridge that gap. So first set of failures that we saw were in execution. These are majorly because of features that were supported in Hive but not supported in Spark. I've listed down a few of them here. So first being the DDL support, it's not on par in Hive and Spark. So there are certain patterns that Hive supports. For example, Hive alter table drop partition using a comparator. Right, and alter table clustered by, which is basically used to change the clustering key of a table. So these are not supported in Spark at all. So what we did was we added support for Hive driver in our SparkSQL runner application code. So any such patterns in the payload, instead of running it via spark.sql, we ran it via Hive driver. Secondly, Hive built-in functions, they couldn't be used as it is in Spark. They required an explicit registration or they would fail with function not found. So we added implicit registry of Hive functions in Spark, and the discovery order that we kept was Spark built-in, Hive built-in, and then any user-defined functions. Order by group by non-orderable data types was also not supported in Spark. Non-orderable types means like maps or structs, etc. So for this, we ported an open PR from open source, right, and that worked fine for us. I've linked the PR here. And lastly, we also saw out-of-memory errors in some cases, and this was majorly because of the extra shuffle that we had introduced when we migrated queries from Hive to Spark to reduce the number of files. So here, just reducing the target size and in some cases increasing the executor memory slightly helped resolve most of the issues. Secondly, we saw a lot of failures in data validation because of difference in behavior in Hive and Spark. Right, so here our overall strategy was to handle this difference in behavior in the translation layer itself. Right, for example, suppose there's a payload which is using cast as varchar, right? So this is not supported in Spark. But effectively what it does is it casts a column into string and then truncates it to a certain character length. So this can be expressed with substring, using substring and then casting as string, right? So we handled it in the translation layer. If we couldn't handle a particular failure in translation, we added the Hive compatible behavior in Spark behind a config. So that meant, and then enable that config only for certain workflows or only for Hive to Spark migrated workflows. Right, so the first two are examples of that. So Boolean to string casting in the timestamp to begin casting doesn't work, works differently in Hive and Spark. So we added the Hive compatible behavior in Spark Chamber and set the config for these workflows. Another point I would like to mention is the partition schema versus Parquet schema. So Hive prefers partition schema over Parquet schema. What that means is if a column is present in the Parquet file, it would, and it's not present in partition schema, it would return null for those columns, while Spark returns the actual value from the file. Now we thought that this behavior is actually makes more sense in Spark, right? So we just identified these columns and excluded them from data validation instead of coding this behavior in Spark. Lastly, in some of the scenarios, we saw that Hive built-in's behavior was different from Spark built-ins. To handle these things, we registered Hive built-in as a temporary function in the payload and then used it throughout the payload instead of using Spark built-in. So that gave us the same behavior. In some scenarios, we also saw performance degradation. For example, if there was a not in or in the query, which translates to broadcast nested loop join in Spark's plan. So these kind of queries degraded. So the only option here was to actually do a query rewrite and replace not in and in with not exists and exists. We also saw performance degradation when a payload was writing to a ORC table, because when Hive merges ORC files into bigger files, it does a metadata operation which is quite efficient, while Spark triggers a shuffle stage, right, which increases the runtime significantly. So ORC, actually we have deprecated at Uber in favor of Parquet, and we had very last few tables which are still using ORC. So we've not yet solved this problem. Lastly, stats auto-gather. So whenever we migrated a Spark workflow, in some of the scenarios, we saw that the downstream Hive workflows degraded, because Hive relies on table statistics to determine whether to do a map side join or a sort merge join, right? So, and because Spark was not computing those statistics, it ended up using sort merge join. So we also had to add support for computing and writing Hive usable stats in Spark, at least for the duration we are using both Spark and Hive on Spark. There are a couple of other problems that I would like to talk about, which do not fall in any of the previous categories. First being small files. So when we migrated Hive queries initially migrated some of the Hive queries to Spark, we saw that the number of output files increased significantly. And this caused namespace quota issues for the users. So Hive solves this by running an additional map-only stage at the end of the query, which basically reads the output files of the previous stage and combines them into bigger files and writes them back, right? To solve this in Spark, we used rebalance. So for all the SparkSQL queries, we added the rebalance node in the logical plan of the query just before the data writing command. So this, so if you look at this original plan, it has a create data source table as select command. It becomes this. We add the rebalance partitions node just before writing to the table. We also had to tweak a couple of AQE rules, that is coalesce and optimize queue, to work with the file target size, so that we can create bigger partitions at the end, at the last shuffle, right? Or maybe 1 GB, 2 GB, or 5 GB partitions without impacting the previous stages and the parallelism of the job. And yeah, lastly, bucketed tables. So Hive and Spark both use different hashing algorithms when they write to bucketed tables. Hive uses Java-based hash and Spark uses murmur hash. Although Spark supports writing to both Hive bucketed tables and Spark bucketed tables, but the problem was that when it wrote to Hive bucketed tables, it ended up creating too many files. That was because the data amongst the tasks was distributed using murmur hash, and then it was redistributed using Hive hash into the bucketed tables. So effectively, it ended up creating number of tasks multiplied by number of buckets files, which can blow up very fast. And lastly, Presto also does not support reading Spark bucketed tables. So we decided to go with Hive hash, as majority of our read use cases were in Presto. And to solve the small file problems, we added support for Hive hash in the rebalance node, so that data amongst the tasks is also distributed using Hive hash. We also plan to extend this support in rest of the shuffle stages in case we want to use the bucketed table optimizations in the read path as well. So these were the results. We were able to migrate 100% of the interactive workloads and 80% of the ETL workflows, which contribute to about 4 million monthly queries. And we saw 50% of reduction in both runtime and cost across all the migrated workflows. And we were able to release a lot of yarn capacity back. Talking about the future work, we are yet to migrate these select kind of queries which directly connect to HS2 and fetch the results back. So we need to provide the similar JDBC, ODBC connection for interface for SparkSQL. Mostly we'll be using Spark Thrift Server for the same. Secondly, fast fail on semantic issues. Right now we get to know any semantic issues once the yarn job is launched. We should be able to leverage the same Spark Thrift Server for the same by running a quick explain on the query and then actually launch the yarn job. Thirdly, we also, so as I mentioned earlier, we introduced a rebalance node which basically shuffles the data, right? Because of that, for some of the data sets, we saw a significant increase in the output size. That is because we are shuffling the data randomly, and this might increase the entropy of the data and reduce the efficacy of the compression algorithm and the run length encoding in Parquet files. And lastly, when we migrated from Hive to Spark, we saw some of the downstream workflows failing with file not found exception, specifically in cases where writes and reads happen concurrently. This is because Hive, when it overwrites a partition or table, it uses the same file name convention. So the reads might not even get to know that the table has been overwritten. But Spark generates a new file name every time. So although earlier reads were probably reading inconsistent data, but users only complain when their jobs fail. So we are working on solving this as well to support the in-flight reads. So that's about it. Thanks a lot for joining the session.